Okay, so now let's continue with our lecture, which is a couple of more interesting stories with the memories. Okay, this slide actually explains what we are trying to do here, uh, but we have also showed you in the marks what they are. Like, make sure you include path. If something goes wrong, first thing that make sure your same directory as this exp9.asm has also this macro.asm. You can use this from whatever latest CS47 macro.asm you have. And also I talked about this forcing a data section, which is default to the mars as 10010000. It's basically we are forcing to the base address in the static data section of the MIPS. All right. Now, interesting two slides. Endianness, big endian or little endian. So this is something to do with, remember, like what I said in a couple of previous slides, through the previous slides, is that from processor perspective, a memory is a byte addressable device. Okay, means each address contains a 1 byte, and then if you are storing a complete word in a location, let's say 10010000 in that location, a complete word, but that address belongs to a byte. So where the other bytes will go, because a word has 4 bytes, right? Those 4 bytes will be stored in successive higher addresses. Like, so one address from, let's say we are writing from 10010004 a complete word, so that complete word will span across 4, 004, 005, 006 and 007, that 4 byte. Now the question is, what shall I put in this lower address? Shall I go with the lowest byte of the whole world and put it there, then second lowest byte, then other higher bytes and most significant byte at the highest address, or other way? Okay, so that is the dilemma. Okay, so this is all captured in your experiment 10.asm, where we are trying to define some data, like one level var a. Let's say I'm trying to store a byte. Then var b, I'm trying to store a half word. Okay, var c is trying to store a full word, like 76543210. And I'm using the load byte, load half word and load word in the main program. But our most interest is to check how this data being laid out into the memory. Okay, so var a byte, you can say it's a type character in terms of high level programming. Var b, that level belongs to like half word, like a short type of data, native data in Java or C++, and a full word like an integer, 32-bit. Okay, and we want to store them. So what happens here? We have this byte. So your assembler starts from the lowest address. Okay, a byte is stored into that start address, and then next one goes to the next higher available address. So half word goes from 002 and span across 003. Let's say we write it as a 1032. Okay, the lower half goes to the lower address, higher half goes to the higher address. A full word, similarly, let's assume lower half go to the lower address and higher parts go to the higher address. So lower byte to the lowest address, starting from 004, and then this is 10, lowest address, 32 next higher address, 54 next higher address, 76 next higher address. So that's how, let's say, it lays down. Now one question, what is this gap for? Why it didn't start from an address like 10010001? Like why this half word after the byte is at 10010000? Why it didn't start the next half word laying down from this address? We'll discuss this in the next lecture. Okay, this is another interesting phenomenon of data laying out. Okay, but today let's concentrate on this problem. Like we just assume one way of laying down this data. Now, like this is the way we just thought, right? Now, why not the other way? Like byte, okay, fine, this address, we don't have any other choice. But for the word, why don't I put a higher byte into the lower address and lower byte into the higher address? Nonetheless, it will fill up from the lower to higher. But the point is, which part goes where? Okay, so similarly, the word can be higher word, like higher MSB side, most significant byte side 76 can start from the lower address and go to the higher as we go from left to right. That is our natural direction of reading, writing. So we start from higher, goes to the lower, from left to right. So I want to store this whole variable from an address 10010004. So my natural direction is to make the 76 at that address, then 54 next available address which is higher, and 32 next higher address, 10 next higher address. Okay, so I start my address number from the address I specify and go in our natural direction of writing or reading. The other part, like the previous one, the right hand side part, is that convention saying is that I want to follow this lower half goes to the lower address and upper half goes to the higher address. Okay, so both this part has like undeniable logic, okay, behind them, right? So both are correct, like no one is wrong. So this, the right hand side, we call it as a little endian. Okay, means your lower part, the little part goes in the little address or lower address, and higher part goes to the higher address. Okay, whereas the left hand side camp or ID is called big endian. Big endian says that my higher part starts from the address where I'm trying to store. Incidentally, that becomes your lower address. So lower address starts with the higher part of the word of the multi-byte data is a big endian convention, whereas lower part of multi-byte data goes into the lower address is a little endian convention. Now each processor follows one of the other. Okay, it can follow big endian, it can follow little endian, but whatever it follow, it need to stick to it. And all the compiler assembler around this processor has to follow the same convention. I cannot just bring in a compiler or assembler which follows a little endian convention where my processor is assuming a big endian convention. That will be disastrous. Okay. Modern processor, however, usually like place and switch. Okay, you can either turn on its big endian or turn on as a little endian, but not in between the operation. Only before power up you can actually go and select, or at least before it actually start functioning fully, you need to set that option that, hey, I want to follow big endian. So it operates as a big endian machine, or I want to follow little endian, so it operates as a little endian machine. So that's modern computing system. They want to just like end the fight between these two camp, big endian, little endian, and there is no end in it. Like every party has its valid point, how they want to lay down their memory. Okay, so that's our next experiment, and that's the last part we'll do for this lecture.